In this video, we're going to look at error estimates for the trapezoidal and midpoint rule. So the question here is to apply the trapezoidal rule and the midpoint rule with n equals 5 to estimate the definite integral from 1 to 2 x e to the x dx. Part B of the question asks us to estimate the error bound and compare to the actual exact error by applying the fundamental theorem of calculus. Part C asks us to illustrate with a diagram that the trapezoidal rule overestimates the definite integral from 1 to 2 x e to the x dx, and the midpoint rule underestimates the integral given by integral 1 to 2 x e to the x dx. All right, let's begin. So what we have is the function f of x is equal to x e to the x. The number of partitions are n equals 5. Lower limit of integration, a is equal to 1. Upper limit of integration, b is equal to 2. And delta x is equal to b minus a over n. So delta x is 2 minus 1 divided by 5. 1 over 5 is 0.2. And here we have our equally spaced values of x. We're going to apply the trapezoidal rule to this integral from 1 to 2 x e to the x dx. This is approximately equal to T5, trapezoidal rule with 5 trapezoids. This is delta x, which is 0.2, divided by 2, times f of 1, plus 2 times f of 1.2, plus 2 times f of 1.4, plus 2 times f of 1.6, plus 2 times f of 1.8 plus f of 2. So T5 is equal to 0.2 delta x divided by 2 times f of 1 is 1 e to the 1 because f of x is x e to the x plus 2 times 1.2 e to the 1.2 plus 2 times 1.4 e to the 1.4 plus 2 times 1.6 e to the 1.6 plus 2 times 1.8 e to the 1.8 plus 2 times f of 2, which is going to be 2e squared. So that's just x e to the x. All right, notice how the first and last are only have 1 in the front. So basically it's 1 times f of 1 and 1 times f of 2. And all the middle ones have 2's in them. That's how you remember this. It's like the 22 rule. If we add all of this up, put it into a calculator, we're going to get T5 is equal to 7.44477. This is an estimate to the definite integral from 1 to 2 x e to the x dx. So this is approximately equal to T5, and that's equal to 7.44477. Now we're going to apply the midpoint rule to get another estimate. So the function f of x is equal to x e to the x, same function as before. And the value for the number of intervals is n is equal to 5. Lower limit of integration is a is equal to 1, b is equal to 2, and delta x is equal to b minus a over n. That's 2 minus 1 over 5 is equal to 0.2. Notice for the midpoint rule, we have to average the left and right hand points. So you average 1 and 1.2, and we get 1.1. And we average 1.2 and we have 1.4 here. Let me put this in, 1.4. We average right hand and left hand rule and we get 1.3. And we average 1.4 and 1.6, we get 1.5. And we average 1.6 and 1.8, we get 1.7. And we average 1.8 and 1.2, we get 1.9. So we evaluate the function at the midpoints of every interval. All right, so what we have is integral from 1 to 2, x e to the x dx This is approximately equal to M5, midpoint rule with 5 partitions. That's equal to delta x, that's 0.2, multiplied by the functions evaluated at the midpoint. So it's going to be f of 1.1 plus the functional value evaluated at 1.3 plus f of 1.5 plus f of 1.7 plus f of 1.9. So M5 is equal to 0.2 times f of 1.1, well, f of x is x e to the x. So let's just substitute 1.1 and we get 1.1 e to the 1.1. And f of 1.3 is 1.3 e to the 1.3. f of 1.5 is going to be 1.5 e to the 1.5. f of 1.7 is 1.7 e to the 1.7. f of 1.9 is 1.9 e to the 1.9. M5 comes out to be 7.36122. Let's do some review. The trapezoidal rule approximation T5 comes out to 7.44477. The midpoint rule approximation to the definite integral is 7.36122. All right, so now we're going to do some error-bound approximation. The error estimate formulas are given. Let's find k, which is the maximum of the second derivative. This is the hard part when you're calculating upper bounds for the error. K is equal to maximum of f double prime of x on x between 2 and 1. We need to differentiate the function twice. So f of x is equal to x e to the x. Now differentiate this, we get f prime of x, applying the product rule. Derivative of x is equal to 1 times e to the x plus, keep x the same, times e to the x. Now let's do the second derivative, f double prime of x. That's going to be derivative of e to the x is just itself, e to the x. Now apply the product rule to the second term. Derivative of x is equal to 1 times e to the x plus keep x the same times derivative of the second, which is e to the x. If we simplify this, we get f double prime of x is equal to 2e to the x plus x e to the x. Let's factor out e to the x. We get e to the x times 2 plus x. Now it's clear that this derivative, this second derivative, f double prime of x, is equal to e to the x times 2 plus x is strictly increasing on 1, 2. And if a function is strictly increasing, the maximum value is obtained at the right endpoint. And the right endpoint is x equals 2. So that means f double prime of 2, which is equal to e to the 2 times 2 plus 2, that gives us 4e squared. This is the maximum of the second derivative. This is k. So let me repeat this. Because the second derivative is a strictly increasing function, so on 1, 2, if you were to do a graph of this, when x equals 1, we get e to the 1 times 2 plus 1 is 3. That's going to be 3e. So let's say this is 1 and this is 3e here. If you put 2, 2 plus 2 is 4e squared. That's way out here. So you can see how the second derivative, f double prime, the second derivative is increasing, so the maximum is achieved at the right endpoint. And this value, this value of the second derivative is 4e squared. This is the y value. All right, so now that we have that, we can compute our error bounds for both the midpoint and the trapezoidal rule. So the formulas you can see are essentially identical. The only difference being in the trapezoidal rule you divide by 12, in the midpoint rule you divide by 24. Okay, so for both of the trapezoid and midpoint rule, we have k, which is the maximum of the maximum of the second derivative, and that was computed to be 4e squared. A is equal to 1, the lower limit of integration, b is equal to 2, and n equals 5, the number of partitions. Error trapezoidal is less than or equal to k, which is 4e squared, times 2 minus 1, b minus a, all cubed, divided by 12 times 5 squared. And this is approximately equal to 0.09852. Error midpoint is less than or equal to k, which is the same, 4e squared. b minus a, that's the same, 2 minus 1 cubed. The only difference is we divide by 24. 24 times 5 squared. And if we decimalize this, we're going to get 0.04926. Now, let's apply the fundamental theorem of calculus to compute the actual error. So we need to compute the exact value of the definite integral from 1 to 2 x e to the x dx. Applying integration by parts, we're going to let u be equal to x, du is equal to dx, dv is e to the x dx. Integrate dv to get v. v is equal to e to the x. So we get u times v, which is x e to the x, integrate from 1 to 2, I should say evaluated from 1 to 2, minus the integral from 1 to 2, v times du, that's e to the x, times dx. That's going to give us x e to the x, minus antiderivative of e to the x is itself e to the x. Evaluated from 1 to 2, we apply the fundamental theorem of calculus, put the upper limit in, we get 2e squared minus e squared, minus, put lower limit in, we get 1 e to the 1 minus e to the 1, and that's just e minus e is 0, so the result is 2e squared minus e squared is e squared. Let's approximate that or decimalize it, we get 7.38906. All right, so let's now compare the actual error and the error estimate, the upper bound error estimate for both the trapezoidal rule and the midpoint rule. The error trapezoidal, the exact error is, we can get that from looking at the difference between the definite integral, 1 to 2, x e to the x dx, which we computed, by the way, using integration by parts, minus the trapezoidal approximation, T5. And this comes out to 7.38906 minus T5, we calculated that before, that's 7.44477. So the error trapezoidal actual is going to be minus 0.05571. The error midpoint actual is going to be integral from 1 to 2 x e to the x dx minus m5. That's equal to 7.389. That's the exact value of the definite integral, integral x e to the x dx, which we computed using integration by parts, minus the midpoint approximation, which came out to 7.36122. So the error midpoint, the actual exact error of the midpoint rule is 0.02784. Now, from the error estimate formula, we calculate the upper bound for the error of the trapezoidal rule. That came out to be 0.09852. For the midpoint rule, it came out to be 0.04926. And the error trapezoidal, the exact error, we calculated that to be 0.05571. And for the midpoint rule, the exact error is 0.02784. We've taken absolute values here. Now, notice something, that the upper bound for the error, when we apply the upper bound formula, is larger than the exact error, as it should be, because it's called the upper bound for the error. And the same for the midpoint rule. All right, let's summarize that. In both cases, the error estimate upper bounds are larger than the actual error computed by applying fundamental theorem of calculus. And this is why we call it an upper bound estimate for the error of approximation. Part C of the question asks us to illustrate with a diagram why the trapezoidal rule is an overestimate and the midpoint rule is an underestimate. So let's start by comparing the actual error estimates. We know that the error trapezoidal, the exact error, came out to be minus 0.05571. The midpoint rule, the exact error, came out to be 0.02784. Notice they're opposite signs. And so now we can see that the area trapezoidal is integral x e to the x dx minus t5, and this is less than 0. That means that t5 is larger than integral from 1 to 2 x e to the x dx. That means the trapezoidal rule is overestimating. It's bigger than the actual error. Sorry, it's bigger than the actual area under the curve. So T5 overestimates. Now let's illustrate geometrically with a diagram. We know that the second derivative, f double prime of x, is e to the x times 2 plus x. And for x between 1 to 2, the second derivative is clearly positive. So that means that the function x e to the x is concave up on the interval 1 to 2. And the top base of the trapezoid, the secant line, is going to overestimate. You can see it's trapping more area than it's supposed to. So for that reason, the trapezoidal rule will be overestimating. It's harder to see that with the midpoint rule, but we're going to do that. Now, from the midpoint rule, we can see that we have integral from 1 to 2 x e to the x dx minus m5. This result is positive. What does that mean? That means m5 must be a smaller number than the area under the curve. So m5 is less than the definite integral of 1 to 2 x e to the x dx. That means m5 underestimates. Let's illustrate this with a diagram. We know f of x is concave up, as discussed before. So you can see that a1, this area, is less than a2. And for that reason, the midpoint rule underestimates. It's a little bit hard to see from diagram, but it's clear that a2 has a larger area than a1. And for that reason, the midpoint rule is underestimating. All right, thanks.